All right, what's going on YouTube? What's up? I am so sorry. I know I just realized I am 30 minutes late compared to where I scheduled this stream for. So I see that we do have one viewer waiting. Thank you for waiting if you are still there. I appreciate you and I apologize that we're so late today. So, yeah, a little bit to talk about today. We're going to do something slightly different. I'm excited for today's streams. There's a little sneak peek. So today is day 7. Morning dog. What do you mean, morning dog? What's going on? How's it going? Yeah, so today is day 7, relearning number theory. How's it going, Leo Lectures? Remind me, I'm going to talk about your video a little bit later. It's great. It's fantastic. I really loved watching the ZFC video last night. Yeah, okay, so today is day 7, relearning number theory. We're brushing off mathematics, dusting off these cobwebs. You know, we're going to get back into shape. For anybody who's seeing this for the first time, I studied mathematics, pure mathematics, like about 15 years ago before giving up and making a lot of money in Silicon Valley instead. And now I was affected by the tech layoffs, and so now I've got a lot of free time before I take my new job, and I just want to relearn number theory. I want to build mathematics as a hobby, as a skill that I used to have, and bring it back. You know. Yeah, there's a little short intro. I call myself the math hobbyist. I started putting quotation marks around hobbyist because, like, I don't know how I feel about seeing that all the time. Like, I do have a degree in mathematics. I have taught a lot of people. I have made a lot of money off of mathematics. You know, even if I'm not like a full-time traditional professor or anything like that, like, I don't know. And it is true that the math that I'm studying is a hobby. I don't expect to get many private students trying to study proof theory, like how to write proofs, or people looking for number theory. Like 99% of the people subscribing to my channel right now, which, by the way, thank you everybody, 286. That's crazy for how fast this channel is growing. But yeah, like it feels like 90% of people subscribing are interested in machine learning for the sake of training Skynet and ChatGPT. That's cool. I'll sell you that shovel. I will absolutely teach you not number theory, linear algebra. We will do linear algebra. It is a beautiful form of math, and I love it very much. But I'm going to be showing you the beautiful stuff as well as the Skynet stuff. Okay, so Q&A. Part 1, about 9 a.m. EST right now. First, I wanted to start out with this Q&A that we got from Patricia. Shoutouts to Patricia. I wrote this in. BFF of the channel. Thank you, Patricia, for being part of this journey. She was part of my... has been an active community member in my guitar channel as well before this math practice channel. So I did something very similar but different, practicing live classical guitar. And now I'm trying to take that idea of a practice stream over here to mathematics. But yeah, anyway, so question was best foundations books. That's the short of it. I should have gotten the exact phrasing, but I guess it doesn't matter that much. I'll pull it up. She asked, like, how do you recommend to study foundations? Like, you have a lot of great recommendations. You have a lot of great recommendations for high-level math books, but I need to work on my fundamentals. Where is it? Oh, yeah, here it is. She says, I'm loving, on yesterday's video, I'm loving these videos. In earlier ones, you have made several suggestions for books on different areas of math and for practice problems. My foundations for math from high school and college are weak. Can you make some suggestions on books for basic maths like algebra, geometry, and trigonometry? Short answer, no. I don't know. Longer answer, Yes. So what I would recommend for books, I've heard of this book by Blitzer. This one looks nice from what I've seen. And I think that that's college algebra. Um, and this looks like a nice older classic text. I would take a look at that one. I don't know. Yeah, honestly, I don't know. I don't have a lot of recommendations. I found there's another math YouTuber named the Math Sorcerer. I wish I could find their exact handle. Where is it? Yeah, at the Math Sorcerer. So at the Math Sorcerer, recommends Blitzer. He recommends that one. He recommends a couple of others. I can't give you great recommendations myself. So this one looks good to me. Algebra and Trig.
Once you get through,
Take a look at Blitzer, and then also take a look into Hornsby. This one looks nice to me. This is algebra and trigonometry together. That's if you want a book. But my recommendation is don't do any of that, actually. What you can do instead is check out... First, just go download the SAT tests. I was tutoring a student, like an adult hobbyist student, and his goal was to solve the SAT. He didn't do well in the SAT a long time ago in high school, and for his own confidence, he wants to retake the SAT and get a better score. I think that's freaking beautiful, y'all. I think that's awesome. So I was so happy to be tutoring him. Our schedules got out of line and work got busier for him or something, so we're not working together at the moment, but Tom, let's get started again. It would be fun. I know you're watching these. Just download the SAT practice tests. Get those, and I think you'll be pleasantly surprised at how much you remember. Just get started is my answer. That's my short answer. Download the SAT practice tests, run through it. You'll be pleasantly surprised at how much you remember. And for the things that you get stuck on or that you almost remember but you're not able to solve the problem yet, those practice tests have solutions and explanations for how to solve those problems. So I think that that's the best place. Like, you'll be surprised. Yeah, so go try them yourself first, and then go watch my videos doing it. sat.themathhobbyist.com. That will be a URL that'll just jump you straight to my SAT Foundations series. So I just renamed it, not Foundations, Fundamentals. Foundations, quote unquote, means something different in math that hopefully we'll be getting into at some point. But yeah, on Saturdays, get it? SAT Saturdays. I plan on working through fundamentals like college algebra, SAT math, running through practice tests, things like that. And so, yeah, I have one video so far. It's titled something clickbaity like, can I get a perfect score on the SAT? So go check it out. I had a lot of fun filming that video the other day. So if you want to brush up on your fundamentals, go check out those videos. I wish that you could subscribe to like one playlist, because some people might only be interested in that and they're not interested in number theory, or somebody's only interested in linear algebra and not interested in anything else, etc. So, yeah, that's my short answer. And then finally, one more answer, actually. I keep lying to you, saying that just one more. But last one is, don't worry. don't worry, actually. Don't worry about it. Like, chatting with Patricia yesterday, she was saying, like, oh, like, my family members, they all know Calculus 3 and differential equations, and they studied thermodynamics. It's going to be a while until I can catch up with them. And I'm like, no, like, I bet you that they've never seen the fundamental theorem of arithmetic before. I guarantee you, like, that all of those engineers in your life, like, you know some math that they don't know. And you don't need anything else. Like, this series, this Intro to Proofs and Number Theory series is self-contained. It does not, like, literally, that is what number theory means. It's like, we are just studying integers, like whole numbers. You don't even need the square root of 2, usually. Like, you don't need anything from calculus. You don't need differential equations. We're going to be studying the counting numbers, and it's going to get complicated. Don't get me wrong. That doesn't mean it's easy. But this series is actually self-contained. And you're already learning some math that most people never see. Which I think is freaking cool. Like, number theory is the queen of mathematics, y'all. Like, number theory is where it's at. It's the most beautiful math. But even amongst mathematicians, it's optional. Like, it's not fundamental even to mathematicians. Like, it is an elective at most universities, I think. You don't have to study number theory. And most Intro to Proofs classes will teach you a little bit about number theory, but they're not going to do a deep dive like what we're going to do. Yeah, so there's my little motivational pep talk for your excellent question. Thank you for writing in. Please, everybody, leave a comment below, pause the video. If you have any questions at any time, drop a comment, and I will respond to those at the beginning of these videos. Cool. Now, speaking of, I got a couple chats from Leo Lectures. Shout out to Leo Lectures, another BFF of the channel. I don't know if this is your short handle, but I assume so. At Leo Lectures. Very cool. 2 videos so far. Brand new YouTuber. Awesome stuff. I really enjoyed the ZFC video, and then there's another one about the axiom of choice that looks really cool. I'm not gonna lie, I fell asleep, like, deliberately to the ZFC video last night, so I'm gonna have to watch it again with, like, a little bit more of an awake mind and, take notes or something, who knows. But it sounded really awesome. I really liked it. So Leo Lectures is legit. He's doing, like, axiomatic, pure mathematics. Axiomatic. And literally, the word axiom is in the second video. Literally, ZFC is the building blocks. Mathematicians, we love to play chess and just get more and more abstract and pointless and philosophical. Right now, ZFC is what we have all agreed on as the foundational things. Like, everything of mathematics is built off of this set of axioms. And it is things like the fact that you can have an empty set, that 2 sets are equal if their elements are equal. I remember that from you. Thank you. And yeah, my ASMR ass. Exactly, yeah. Or fall asleep. Like, what's the term for that? Like a fall asleep video or whatever. Like rain sounds. Background mathematics. That's how nerdy I am, dude. That is how nerdy I am. Yeah, here, let me at least write this. Like, set A equals set B if A equals B. Something like that. I don't know. Those are, like, 2 axioms that I remember. All right, so, and I was going to read his comment earlier. Problem with looking for foundations books is that that mathematicians will name a book on algebraic number theory, Intro to Arithmetic. Exactly. Yeah, exactly. If you follow my channel and you are looking to brush up on your arithmetic, be careful, because over here, this is the kind of channel where I will be pulling out these two books at the same time. Where's the other one? Damn it. Oh, here it is. I will literally be working on both of these books, okay? We will be looking at shortcut math. This might be good for anybody. Add and subtract and multiply numbers really quickly. It looks just like this other book, and it sounds just like this other book. But if you ignore the graduate text in mathematics, it looks exactly like this one, shortcut math. But this one is insane. This book is like the hardest book you'll ever read in your life. It's gorgeous. Like the first page, you're just like marveling in the beauty of this book. And every mathematician I've worked with who, like the one who recommended this book to me for my undergraduate research, he was like, every book by Sarah, every word is worth its weight in gold. And I was like, okay. So, yeah, Sarah is a G. Exactly, right? So, Leah Lectures is right. The problem with like looking for foundations books is, or fundamentals is that mathematicians will title them scary sounding things and recommend the wrong one. So stay here, stay safe. This channel, I promise I'm going to try to be relatively self-contained. Not gonna lie, we're not gonna be axiomatic. I'm gonna skip ahead all the time because this is my study time. I am self-studying mathematics again, and I don't want to go through every little proof along the way. I'm gonna jump around. So maybe I'm not a pure mathematician. I don't know. Maybe not. But we will be jumping around. And so to that point, today we are going to revisit the proof that we did yesterday on the fundamental theorem of arithmetic. Beautiful. Anytime that there's a theorem called the fundamental theorem of, it's a big deal. This one proves that prime numbers are like the atoms of the mathematical universe, and every number consists of atoms of these primes. That's my layman description of it, but yesterday I carefully wrote out exactly how Andrews proves this theorem from this book. And I wrote it out word for word. Today I'm going to see if I can recreate that proof myself. We'll see. Maybe not. I might get stuck. And then we're going to just jump, several chapters. I think that this is like chapter 9 or something of Andrews. And I was expecting to be stumped, just like memorizing and writing down the proof of FTA yesterday, but we were pleasantly surprised that FTA is way more self-contained than I expected. So I want to actually jump forward to something where I'm not going to understand the proof deliberately, and I am just getting the muscle memory, like, okay, I don't need to understand it, but I can copy this proof, and eventually we're going to meet in the middle. And after writing it down enough times and going back and studying the prerequisites, eventually we're going to understand this treasure. Quadratic Reciprocity by Gauss. Cool. So that's a goal. That's part 1. If we go way back to one of my first thoughts, today I actually have an appointment in between these two streams, so we're going to have to split this stream in half. It's cool because I was already thinking of doing that anyways. Like literally, I had already planned 2 separate streams. And then I was like, oh, wait a minute, I have to, because I have an appointment. Cool, let's do it. Perfect opportunity. So, part 1, we're going to revisit these proofs. I'm going to answer that Q&A, done. And then in part 2, later on today, I will be just live practicing problems. And I'm going to stop yapping. I'm just going to stop ranting at the camera like a madman. and we're just going to be working through these books, and I'm just going to be practicing problems. And then we might be listening ASMR style to some other math YouTubers while we do it. In particular, I'm so excited. Let me know, Leah Lectures. Have you seen City Tutoring yet? I'm obsessed with this YouTuber right now. I don't want to spoil it. Don't watch his videos in between the streams if you haven't seen them. But yeah, like I can give some recommendations, and we'll have some background math. I might listen. We should listen to your ZFC video as well while I like practice and just like. Oh yeah, okay, good. City Tutoring. All right, you don't know who it is. All right, don't worry. Just wait until my video later on and watch it after the fact if you need to. Okay, so this looks like a complete mess. Let's just get started. All right, let's see. Can a hobbyist prove the fundamental theorem of arithmetic? All right, who knows? I don't know. Let's see. How rigorous can I get this statement? Theorem. Fundamental. This is called spaced repetition, everybody, and it's so useful. I wish I knew about it in college. Just do the same homework exercise multiple times. Practice it until it just becomes second nature. Yeah, like do it the next day, and then do it a week later, and then do it a month later, and then do it a year later. If it keeps coming easily to you, just increase the space until the next time you repeat the thing. It's a great technique. Check out the app Anki if you're interested in spaced repetition. All right. Theorem, fundamental theorem of arithmetic. For any integer a greater than 1, okay, I'm pretty sure that that's the statement. I think I'm okay. Cool, man. Gotta head out. Yeah, dude. Good to see you. Thanks for stopping by. And I agree. 95% of the time, you don't go through every detail. Yeah, you never go all the way down to the axioms. You have to create black boxes, and you're like, okay, remember. Let's assume this theorem, then we can get this new theorem. Especially in research. All right, what else? I remember my professor defining Sayre quotients in a graduate class and then going, I'm pretty sure Sayre was 20 when he came up with this. Yeah. I'm pretty confident that Gauss proved quadratic reciprocity when he was 19. Let's write it down right here. Gauss, when he was 19, proved this Mona Lisa theorem, which is crazy. That's crazy. So, okay, I think that this is a accurate statement of FTA. Let's try to get the proof. First, we will prove existence by strong induction. Okay. How does this go? Okay, how does this go? All right, ... and then next we prove uniqueness by strong Next, we prove uniqueness by strong induction and the fact that if P divides AB and P does not divide A, then P divides B. I'm pretty sure that those are the two key ideas. And yesterday I pointed out, like, hey, this is freaking cool. You can get existence just with section 1.1. Like, just knowing what mathematical induction is, this proof, this half of the proof, doesn't have any other prerequisites. This is like literally section 1.1 of Andrews. This fact takes a little bit longer to get to, but this is why this theorem isn't until like chapter 5 or something. I don't know. I have no idea. 5.5, whatever. Something. Anyways, pretty confident that these are strategies that we want. I know that on uniqueness, suppose A is equal to P1, P2, ... Pn, and it also equals another product of primes. Like a sequence of primes pi and a sequence of primes qj. We show that okay, yeah. For uniqueness, we get something like then A equals P1 times P2 ... Pn. Q1 times Q2 ... Qm. By inductive shoot, I thought I was going to be able to remember how this goes. I know that these are the basic facts. I'm about to give up. We'll try again tomorrow. Or soon, and we'll see. I know that we're going to end up like by the inductive hypothesis, we have like 1 is less than I think that the inductive hypothesis applies to P2 through Pn multiplied together. Oh wait. Okay, in Andrew's notation, he does something like 1 less than n less than or equal to k. I'm going to avoid n here. I'm going to, I don't know, commit a sin and use x. X is for all x between between 2 and some number k, we assume the uniqueness property. And at this point, we should have already proved existence. But yeah, so we assume x is uniquely factored up to some point. Then we consider k plus 1 by part 1 existence. We show that this kind of step that I was doing, by the existence proof, we show that 2 factorizations are equal. Hence, we get uniqueness. So say that k plus 1 equals p1, p2, pn, and it also equals another factorization, q1, q2, qm. Then we get this. Since P1 is greater than or equal to 2, because remember that primes cannot be 1. Every prime is greater than or equal to 2. I'm going to say that P2 ... Pn has to be strictly less than k plus 1. By the inductive hypothesis, and same with q2 ... qm. So they are equal? Something feels wrong. This is not how he proved it, but this feels like it is working. So since P1 is greater than or equal to 2 and Q1 is greater than or equal to 2, then the remainder is the inductive hypothesis, like existence and uniqueness applies. So then they're equal. Then K plus 1 equals P1 times, geez, these are unique, and now, like, yeah, I'll just, since the second term is equal, then P2 dot 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 Pn equals Q1 times P2 dot 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 Pn. Yeah, the second term of these things are equal. So now I'm replacing all those Q2 through Qm with P2 through Pn. Does all this work? I think that this works because I can assume that P1 right here, that these are ordered. I think I'm allowed to claim that these are ordered. Q1, Q2, QM. Yeah, I'm allowed to say that these are ordered. So then the second, if we treat this as like P1 times the rest and then Q1 times the rest, then I don't know why that matters. Yeah. I don't know if that's accurate. Then these are equal. Then since they're equal, P1 has to equal Q1, and we're done. Boom. That's rough. Okay. There's uniqueness. It's not correct. Don't learn from me. Do not learn from me. All right, so by induction, let's just go ahead and state the base case. Dang it. All right, it's close. Base case. K equals 2. K equals 2. I mean, that's really all you need. Like, maybe you need to show this for the first non-prime number, which is 2 times 2. But I think that you can technically just... I think that you can just claim that the base case works for P1 equals 1. Like, it doesn't matter. Like, Andrews kind of avoids this problem by just showing a bunch just for fun. Like when, like, we've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. He just shows this table to illustrate that it's true for multiple, like 2 times 2, 2 times 3, 2 times 2 times 2, 2 times 5, and 2 times 2 times 3. And then the other ones are primes. Oh, wait, oops. 9 is 3 times 3. Cool. So he avoids the problem of, do you choose the base case to be 4 or do you choose it to be 2? Doesn't matter. Like, either one, I think, is satisfactory. But then assume The inductive hypothesis for all numbers between 2 and some number k, like let's assume that this thing works, that this claim works, that we can factor a number into a product of primes, and we've seen that it works at least for one of them. I could say 2. Between 2, like what is the last domino that we've toppled over by hitting the first one? We've at least shown that 2 is uniquely can be factored. That there exists a factorization of 2. It is just 2. We wish to show k plus 1 can be factored. Either it is prime, and we're done, boom, or not. If not, k plus 1 equals AB for some AB integers. Then the inductive hypothesis applies to A and B. So k plus 1 equals P1 multiplied up to Pn and Q1 multiplied up to Qm. Let's copy this. Let's do a magic trick. Oh my gosh. Okay, whoops. All right. Reordering, because xy equals yx for all xy integers. We have commutativity. K plus 1 equals reordering. The notation gets weird. Yeah, the notation gets weird if I keep P's and Q's here, so I'm just going to go ahead. Reordering and relabeling. Relabeling. L1, L2, dot, 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 L. Whatever, who cares, alpha. We have some number, we have, like, maybe this is like P1 times Q1 times P2 times P3 times Q2 times P4. I don't know. Something like that, you know? Like maybe A is, just to illustrate and give an example of what the hell are you doing, John? Maybe A is P1 equals 2, P2 equals 2, P3 equals 2, P4 equals 2. Okay? All of those are ordered. And then B might be 2 times 3. Oh wait, no, I wanted something bigger. Whatever, 2 times 11. Okay? Then we reorder that 2, that Q, that P, that P. Well, what am I doing? What am I doing here? All right. There. Oh, I missed another. I had P going out of order. Doesn't matter. I think you all see what I'm doing. Let's pick another prime P4 that is greater than. Okay, here we go. This is not a proof. This is not a rigorous proof. This is not part of the proof. This part is just an example of what I'm doing and what I call relabeling and reordering. So be clear about that. Do not write this down as a proof. Okay. We're getting somewhere here. I wanted A to be less than B. P4 maybe is, can we get this to work? 5? I'm like getting nerd sniped right now, everybody. So A is, I'm literally getting nerd sniped. A is 40. No, A is 40. And I wanted B to be greater than A, but I wanted the prime Q2. This didn't work. Whatever. Who cares? 2 times 11. Who cares? I think you see what I'm doing. Let's just move on. Who cares? Doesn't matter. Reordering and relabeling, we're going to call this K plus 1 is L1, L2, ... L alpha, maybe LR, to stay in the ASCII character set. And existence is established. Rough, but I think that this is a full proof. Let's go back to our notes from yesterday. What is the precise proof? Let's see how it goes. By Andrews. And proofs are it never matters like exactly the phrasing and statement, but like the basic logical idea is what matters. Like, did we get the important steps? And I know my uniqueness proof went differently than his, so I think that there's a flaw in my argument somewhere. All right, proof. Our first goal is to prove that each integer has at least one prime factorization. Note that this works for a few base cases. Let us now assume that each integer up to k can be factored into primes. Then k plus 1 is prime or it is not. So I got this. K plus 1 is prime or it is not. If it is prime, then its prime factorization is itself. I got that. If it is not prime, then k plus 1 equals ab for, I was saying, I didn't write it down explicitly like this. Maybe I did. Maybe I think I said it verbally, but I think we can see that that A and B are both less than k plus 1 because because we have a prime factorization. We have a factorization by the fact that it is not prime, The fact that it's not prime means that there is a factorization AB where A is not equal to, where A is greater than 1. We can say A greater than 1 and B less than the number k plus 1. That is like the definition of being prime. So since 1 is between, or since A is less than or equal to K and B is less than or equal to K, both A and B have prime factorizations, say this and this, therefore K plus 1 is the 2 multiplied together. I used Q's instead of P primes. I don't like prime primes. That's kind of weird. Hence, K plus 1 has a prime factorization. Thus, we have established by mathematical induction that every integer greater than 1 has a prime factorization. Okay, all right, so I got the basic ideas here, and I'm actually going to criticize Andrews because he got to this step, and what I did was I then did this labeling and reordering, relabeling, reordering thing. I suppose these have S and T, so we know that precisely there are S plus T primes here. But what I'm going to criticize about Andrew's proof is that the statement says that a number can be written as a factorization of primes with this ordering, like where every prime is in order. So for the existence proof, he did not show that this K plus 1 factorization is in order. That is an extra step that I added and he missed. So, all right. I didn't think that I was going to get existence. I stumbled for a second there. We jumped right to uniqueness. Now let's compare mine to his on uniqueness. To complete the theorem, we must establish a uniqueness of factorization. Again, we proceed by mathematical induction. Our table also tells us that the factorization up till 12 is unique. How are we on time? I've got 15 minutes. Assume that each integer has a unique factorization. Suppose that k plus 1 has 2 different prime factorizations. Since q1 divides k plus 1, we see that q1 divides... So, since q1 divides k plus 1, then q1 divides the prime factorization of k plus 1. Therefore, q1 divides pi for some I by this corollary. Since both q1 and pi are primes, we conclude that q1 equals whichever prime it is that it divided. Yeah. Clearly, we may reverse the preceding argument to show that P1 equals Qj for some j, hence P1 equals Qj greater than or equal to Q1, and Q1 equal Pi greater than or equal to P1. Therefore, we show that P1 is equal to Q1. Thus, this thing is an integer, not exceeding k. P2 through Pu is this thing. By induction hypothesis, u equals v. And like continuing this process, q2 equals p2, q3 equals p3, ... and each of them are equal. It works. What is wrong with my argument? Because I had P1, P2 dot 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 Pn equals Q1 Q2 dot 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 Qm. And by inductive hypothesis, say if we relabeled these like as P1, I think I've been using A's in other places, but it doesn't matter. Let's use it again here. The inductive hypothesis applies to A and B, right? Because they're both are less than k plus 1, i.e. less than or equal to k. So A equals B, and they both equal some factorization P2 through Pn. Then k plus 1 equals P1 P2 to Pn, and it also equals Q1 P2 dot 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 Pn. I've replaced B with A in this part. I suppose we need here that if AB equals AC, then, and I thought this, but I didn't state it out loud. I got this wrong. If AB equals CB, then A equals C. Is that true? That's not true. Anytime that B is not equal to... Anytime that B is greater than 0. Because if B were 0, then 1 times 0 equals 2 times 0. So what I was about to write was wrong. But as long as B is greater than 0 and an integer, then this fact is true, right? So then, therefore, we get P1 equals Q1, and then, yeah, I like my proof better. I think it's better. I literally think my proof is right and better. So, boom. Can a hobbyist improve on George Andrews' proof of the fundamental theorem of arithmetic? Maybe. I think that the lemma that I used there is also simpler. It like very... it certainly requires strong mathematical induction because, but so did Andrews. Neat. Hey, I feel good. I thought I was totally stuck and wasn't going to get it, but I think it's accurate. Please leave a comment below if anybody sees a flaw in my proof, because I don't know. Yeah. I remember the proof in my number theory course in undergrad being like a lot fiddlier. Like the one in Rosin is just like super fiddly. Like there's a lot of subscripts. I remember a table like drawing out, like the professor drawing out like a huge like a table to kind of... I think it's because Rosin's statement is more like P1 alpha 1. It uses like exponents for every prime, whereas what I haven't seen before is that Andrews just allows P1 to be potentially equal to P2, and I think that that's clever and cleans up the proof a lot. So I think Rosin shows it this way, where Pi is less than Pj. for, yeah, strictly less, not less than or equal. So, hope that makes sense. Oh my god, did we lose the iPad? How long ago have we lost the iPad? Why? No. AirPlay has still been running. What the heck is going on? What? Why did we lose the iPad? How long ago did we? This is so confusing. Streaming is hard, everybody. Like, you think that you've, like, figured it all out. Oh my gosh. You feel like you figured it all out, and then every day something goes wrong. Oh well. I apologize. I'll just skim through my hobbyist proof here. We prove existence by strong induction. We have a base case, whether it's 4 or 2 doesn't matter. It's true somewhere. Every k plus 1 can be factored. Either it is prime. I suppose here we want a base case where it is prime. So clearly if k equals 2. Or a base case where it's not. If not, then k plus 1 equals the multiplication of 2 integers. Then the inductive hypothesis applies to both. A is less than or equal to k, and b is less than or equal to k. So then k plus 1 equals a product of 2 factorizations. Reordering them and relabeling them, now we have those primes in order, and existence is established. Then we prove uniqueness by strong induction. I didn't use exactly that fact, but I remember that's how Andrews did it, so that's how I started. Suppose that A is 2 different factorizations with P's and Q's. And then we can group by associativity P1 times the product P2 through Pn and Q1 times the product of Q2 through Qm. By the inductive hypothesis, we... What the heck? Okay, I would rewrite some of that. That's a little confusing. Yeah, I would erase some of that other stuff. Here's where it really matters. Since P1 has to be greater than or equal to 2, and Q1 has to be greater than or equal to 2, what's the term? Quotient? Or the, whatever. Those two must be, what? Oh, yeah, by the inductive hypothesis, this thing is less than k plus 1, and this thing is less than k plus 1. So the inductive hypothesis applies to every number less than k plus 1. So by inductive hypothesis, these two are equal. Then k plus 1 equals p1 times blah, blah, blah. We replace those q's with p's, with the equal p's. Then P1 has to equal Q1 because A times B equals A times C implies that... oh wait, whoops, I wrote that backwards. A times B equals C times B implies that A equals C, assuming... Oh gosh, okay. A, B equals CB and B greater than 0 implies that A equals C. This is the the lemma that I need for my proof, and I think it's way simpler. I think it would be way simpler to prove that one than the other corollary that Andrews required. Cool. All right. I think it worked. Boom. Done. All right. Now, I said I wanted to revisit quadratic reciprocity as a statement. I'm going to write down as much of the proof today, right now, that I can. And we may not get as far as I wanted, but we'll see. Let's get some muscle memory in our fingers on how this goes. Jeffrey, it's good to see you. It's always good to see you, dude. I hope you're enjoying this stuff. Let me know if you are. Okay. So Gauss's quadratic reciprocity law. Theorem. Quadratic reciprocity law. If P and Q are distinct odd primes, then the Legendre symbol P by Q equals Q by P unless P is congruent to Q, it's congruent to 3 mod 4, in which case they're not equal. I'm just going to go ahead. I mentioned this. That's kind of redundant and unnecessary. If P and Q are distinct odd primes, then these two are equal unless... No, it is necessary. In which case they are not equal. Because if you didn't state this part, then it's possible that sometimes they're equal and then other times are not equal. So it is important. Okay. This could be reframed as an if and only if P... Whatever. There's a way to reformulate that as an if and only if. I'm running out of time. Let's go. Let's do this. Proof. Not going to understand this. And that's okay. This, first we have a remark. This theorem may be established, may be stated, stated equivalently in the form P by Q, Q by P equals -1 raised to the P minus 1, Q minus 1 divided by 4. Okay, I don't see why, but we will understand in the future. Proof. Let mu1 denote the number of integers in the set Q to Q 1/2 P minus 1 times Q with negative least residues modulo p. I used to understand this kind of thing, y'all. I used to understand this. Let mu2 denote the number of integers in the set. Oops. P 2p 1/2 q minus 1 times p with negative least residues. I gotta go like right now. With negative least residues modulo q. Gauss's lemma implies that p by q, Legendre symbol, -1 mu2 and q Legendre p -1 to the mu1. Then since p Legendre q equals q Legendre p, if and only if, there's one of those, if and only if p q q p equals 1, we see that p Legendre q equals q Legendre p if and only if, again, another one of those that we're learning about, mu1 plus mu2 equals 1. Thus, to prove our theorem, we must show that mu1 plus mu2 is odd if and only if p is congruent to q is congruent to 3 mod 4. So that's, I said that could be stated as an if and only if. And then we proceed geometrically, and there's some more stuff. And I gotta go. Teaser for next time. Thank you everybody for watching. This is an example of a math proof that I definitely do not understand at the moment, but we will understand someday soon. Thanks for watching. This was fun. I hope you all have a great day. Have a beautiful day.